Hello everyone, in this video we're going to take a look at the double pendulum and we're going to use Lagrangian mechanics to derive equations of motion that describe this system under the assumption of small oscillations. So just before we get into the maths of this, let's take a moment to look at the system and define all of the relevant parameters. Now essentially all we have is two massive particles, which are the circles in this diagram up at the top left. And I'm going to say each of those particles has a mass of m. Okay, now we've connected up these two massive particles using two light, effectively massless rods, and I'm going to say the length of each of those rods is L. Okay, and then we kind of pivot the system at this point up at the top there, and just let this system move freely under gravity, and we're going to solve for the time evolution of that system. Now, I'll also just make a note that I'm considering the case where the rods have equal length and the particles have equal masses. You can use all of the same methods I'm going to go through in this video for the more general case where the lengths are different and the masses are different, but the maths, the algebra just turns out to be a lot more time consuming. So I'm going to stick to the simpler case for now. Okay. The parameters that we are going to use to describe the state of the system are these two angles, θ1 and θ2, which are the angles that each of the rods makes with the downwards vertical, right? So the dynamical state of the system is defined by those two angles and their time derivatives. Okay, so there we go. We've set the problem up. So let's start forming the Lagrangian, right? So remember, the Lagrangian, capital L, is basically just the kinetic energy minus the potential energy. Kinetic energy I'm writing as T, potential energy as V. Now, if we think about the kinetic energy first, right? The kinetic energy has two contributions, one from each particle. So let's first think about the particle at the top, which I'm going to call particle 1. This is fairly straightforward because particle 1 is constrained to move along the arc of a circle, right, centered at the pivot at the top there and with a radius of L, right, because it's just connected to that point with a rod of length L. And so it's just doing circular motion. And we know that the tangential velocity, or the linear velocity of a particle doing circular motion, is the radius of the circular motion multiplied by the angular velocity of the particle, right? And putting all that together with the fact that kinetic energy is a half mv squared, we can write our first contribution to the kinetic energy as a half m and then L θ1 dot all squared, because θ1 dot is the angular velocity of the motion of that top particle along the arc of its circle, and L is the radius of that circle. So L θ1 dot is the linear velocity of that particle. So there you go. There's the kinetic energy of the first particle. Now for the second particle, it's a bit more complicated because of the fact that it's joined to the pivot by two rods. And so we can't say it's just constrained to move along an arc of a circle. So I think the best thing to do here is to just use Cartesian coordinates initially. So I'm going to write it as a half m and then x2 dot squared plus y2 dot squared, where x2 and y2 are the Cartesian coordinates of particle 2 down there. Okay, so then what we have to do is express x2 and y2, and hence the time derivatives in terms of the two angles. So let's do that. Now, x2 is basically, let's put the origin of our coordinate system at the pivot up there, right? In that case, x2 is basically the horizontal distance from that point to particle 2, which is that dashed red line that I've just drawn at the top. Now, you can split that into two contributions, right? You can split it into a little contribution at the top and a little contribution at the bottom, like that. And if you add those together, you'll get the total horizontal distance from the origin to particle 2. Fortunately, we've got two nice right-angled triangles, right, which I've formed by drawing those red lines on. The hypotenuse of each of those right-angled triangles is L, so we can just use trigonometry to find those distances. The first one, because the red lines that I've drawn are opposite the respective angles θ1 and θ2, we've got to use sine. So x2 is going to be L sine θ1 plus L sine θ2. And there we go, there's our expression for x2. Now at this point, I'm going to start doing some approximations. Remember I said we're assuming that this system is undergoing small oscillations. And what that means in practice is that theta1 and theta2 and their time derivatives are small. Okay, and so we're going to work up until a certain order in powers of those quantities. Now, if I want to end up with equations of motion that are linear in the various angles and their time derivatives, that means I have to evaluate the Lagrangian to second order, because the way you go from a Lagrangian to an equation of motion is taking a derivative, right? So if we do the Lagrangian to second order, when we then take some derivatives and get the equations of motion, then we'll end up with linearized versions of the equations of motion. And so to summarize all of that, I'm just going to say at the top here, we are working to second order in the angles theta I, where I can be 1 or 2, and also their time derivatives theta I dot, right? So we can use the small angle approximation on these sine terms here and say that sine theta is roughly equal to theta, because if you think about the Taylor expansion of sine theta, the next highest order term is a cubed term, which is higher than we are working to for the purpose of this video. So our x2 is going to be roughly equal to L theta 1 plus L theta 2, because sine theta is roughly theta. Okay, good. So what about y2? Well, we can use a very similar method. It's just instead of sines, we want to use causes this time, because we're looking that the y2 coordinate is the vertical distance. And so we want that bit there plus that bit there. So we just replace the signs with causes. And we are also going to put minus signs in front of them, because I've defined the origin to be at the pivot there. In the state that I've drawn the system, both particles would have a negative y coordinate, right? So y2 is going to be minus L cos theta 1 minus L cos theta 2. If we apply the small angle approximation there, cos theta is roughly 1 minus theta squared over 2. I'm going to have both of those terms if I'm working to second order. If I just plug that approximation in, this is roughly minus L times 1 minus theta 1 squared over 2, and then minus L times 1 minus theta 2 squared over 2. And if I just expand the brackets, I'm going to end up with an L over 2 theta 1 squared, and then an L over 2 theta 2 squared, and then I'm going to get two lots of minus L, and so minus 2L there. So there is our second order version of the y2 coordinate. Now, remember, we're trying to get the kinetic energy, so we want to take a time derivative of x2 and of y2. So let's do that. Now, x2 is pretty straightforward, because our x2 expression was there. If we differentiate that with respect to time, you just have to put a dot on each of the angles, right? So nothing particularly interesting happens there. That's just L theta 1 dot plus L theta 2 dot. Okay. For the y2 term, we've got to think a little bit harder, because you've got these quadratic or squared angle terms. Now, if you think about what happens if you differentiate the first term, well, if you use the ordinary power rule, just bring down that squared power and decrease the power by 1, your first term would turn into, sorry, let me just write here, y2 dot, your first term would turn into L theta 1, right? Just using the standard power rule. But then from the chain rule, right, we have to multiply that by theta 1 dot, because we're really differentiating not with respect to theta 1, but with respect to time. Okay, so this extra theta 1 dot comes from the chain rule. Then the second term is very similar. That is L theta 2 and then theta 2 dot. Again, you get this time derivative appearing from the chain rule. Okay, and actually technically these should both be approximately equal to. Now, what we can see here is that, remember, in the kinetic energy term, right, both of those are squared. The x2 dot and the y2 dot are both squared. Now, if you square x2 dot, you're going to get second order terms in the theta I dots, right? Whereas the y2 dot is already second order, and so if you square it, it's going to become fourth order, and so we're going to be able to actually neglect all of those terms, right? So basically, we're saying that y2 dot squared is much smaller than x2. Is much smaller than x2 dot squared, and so we're just going to ignore the y2 dot squared term. So then, if we take our x2 dot and plug that back into our kinetic energy expression, let's see what happens. Well, our kinetic energy is going to be roughly, if you look back at this expression that we started with, there is a common factor of a half m to all of those terms. So I'm going to take out a half m. Then from this first term, if we just expand those brackets, we get L squared theta 1 dot squared. And then our second term is going to have this x2 dot squared, which is all of that stuff at the top squared, right? So I'm going to have, in fact, why don't I just square that expression now, right? So if we square that expression at the top, you get the first thing squared, so L squared theta 1 dot squared. Then you get twice the product of the two terms, so 2 L theta 1 dot times L theta 2 dot, and then you get the second term squared, which is L squared theta 2 dot squared. All right, now we can just collect terms together and take out another common factor, right? So there's an L squared common to each of these terms because you've got an L and an L there, so they make an L squared as well. So this is actually a half mL squared. And then notice that these first two terms are the same, right? So I get 2 theta 1 dot squared, and then I get 2 theta 1 dot theta 2 dot from the next term, and then I get theta 2 dot squared, just one of them from that final term. So there is our not linearized, our second order kinetic energy expression in terms of the time derivatives of the angles. So now all we've got to do is find the potential energy V, right? Which is a little bit easier actually, because we know the only source of potential energy in this system is gravitational potential energy, which is just mass times gravitational field strength times height. And the heights of the two particles are just their y coordinates, right? So our potential energy is going to be mg, well, we get mg y1 from the top particle and mg y2 from the bottom particle. So I can write our potential energy like that. Okay, now we've already got our approximate form of y2, right? That was down at the bottom left there. That was y2. Okay, y1, we've actually also kind of done that as well, because y1 was just one of the contributions to y2. It was essentially the top vertical red line in that diagram, right? So when I did y2, I added that to another contribution. y1 is just going to be that top vertical line, right? So I can say y1, it's essentially just this term there, right? And if I expand those brackets, I get L over 2 theta 1 squared minus L. And that's going to be our rough expression for y1, right? So then if I just add together that thing and the y2 expression, which is immediately above it, and collect terms together, well, you've got 2 of the theta 1 squared term, but only 1 of the theta 2 squared term. So what I'm going to do is write that. I'll take out the factor of a half, take out the L as well, and then write that as 2 theta 1 squared plus theta 2 squared. And now I'm actually going to ignore all of these constants. You've got a minus 2L and a minus L. I'm just going to say plus a constant, because remember, potential energies are only ever really defined up to a constant because you're free to choose the zero level. And so physically, it doesn't really have a significance. And mathematically, what's going to happen is that when we differentiate the Lagrangian to get an equation of motion, then the constant is going to disappear anyway. So we don't really have to care about what the value of that constant is. So anyway, putting all of that together, what I've got now is that the Lagrangian is roughly half ml squared times 2 theta 1 dot squared plus 2 times the cross term theta 1 dot theta 2 dot plus theta 2 dot squared. And then subtracting all of the all the potential energy gets us minus a half mgl 2 theta 1 squared plus theta 2 squared. So there is our second order Lagrangian. So I've just moved that Lagrangian over to the left of the screen, and all I'm going to do with it is plug it into the Euler-Lagrange equations. Now, I'm not going to derive the Euler-Lagrange equations in this video. If you haven't heard of or seen these before, that might be something that's worth reading up on. For now, I'm just going to quote these equations, which are basically just the way to go from a Lagrangian to a set of equations of motion. And they're as follows: d by dt of the partial derivative of L with respect to theta I dot, where I is again either 1 or 2 in this system, minus the partial derivative of L with respect to theta I itself, is equal to 0, right? So if we plug our Lagrangian L into that set of two equations, it's two equations because I can be 1 or 2, then we will get two equations of motion involving our angles theta 1 and theta 2. So we've got 4 partial derivatives in total to evaluate. And so let's just work out those 4 derivatives and then plug them into the Euler-Lagrange equations. So I'm going to start with partial derivative of L with respect to theta 1 dot. I'm also going to stop using approximately equals signs here. Just for convenience, I'm going to write these as equals signs. But we know we've only worked to second order. All right, so if we take our L expression over on the left and we differentiate it with respect to theta 1 dot, well, you've still got this prefactor of a half ml squared. Then what's going to happen to this first term? It's just going to turn into 4 theta 1 dot using our standard power rule for differentiation, right? So 4 theta 1 dot. The second term here, the coefficient of theta 1 dot is 2 theta 2 dot. So I add on 2 theta 2 dot. And the third term doesn't depend on theta 1 dot at all, so that doesn't contribute anything. And the potential energy part of the Lagrangian doesn't involve any dots at all. It's purely dependent on the angles themselves, so that doesn't contribute anything to this derivative. And I can write this slightly more nicely. It's just ml squared times 2 theta 1 dot plus theta 2 dot. And there we go, we found our first partial derivative. Now, what about if we do a similar thing for theta 2 dot? Well, we'll still get this prefactor half ml squared. This time, the first term doesn't contribute anything. The second term contributes a 2 theta 1 dot. And the third term, if you differentiate that, you bring down the power and you get 2 theta 2 dot again. So this time is pretty similar. It's ml squared, and then it's a little bit more symmetrical. It's just theta 1 dot plus theta 2 dot, like that. Okay, so 2 more derivatives that we have to evaluate. Now let's do dl by d theta 1 itself. Well, this time we don't get any contribution from the first part of the Lagrangian, which was the kinetic energy. We only get a contribution from the potential energy, right? So we get a minus a half mgl. If we differentiate this stuff with respect to theta 1, we just get a 4 theta 1, right, from this 2 theta 1 squared. So this is just multiplied by 4 theta 1. And then if we just do the half times the 4, we get minus minus 2 mgl theta 1. There we go. Now, last derivative we've got to evaluate is dl by d theta 2. It's going to be very similar, except this time, this term is not going to give you any contribution. The second term is going to give you a 2 theta 2, but the 2 that you bring down will cancel with the half in front. And so this will just be minus mgl theta 2. Right, so if we take all of that stuff and plug it into the Euler-Lagrange equations, well, let's first think about the I equals 1 equation, right? So when I equals 1, we care about this derivative and this derivative, right? Because those are the ones involving theta 1 and theta 1 dot. So remember, we also have to do the time derivative of that first partial derivative, right? All that means is that in that expression up at the top, I just have to add a second dot on both of the thetas, because we just take that and we differentiate it with respect to time. So I'm going to get ml squared 2 theta 1 double dot plus theta 2 double dot, right? Then I have to subtract off this one, but it's already negative, so I'm going to get a plus sign there. So it's going to be plus 2 mgl theta 1 is 0. And there we go. Now we can actually make this look a little bit nicer by dividing through by ml squared, right? If we divide through by ml squared, what's going to happen? We will get 2 theta 1 double dot plus theta 2 double dot. The second term is then going to be plus 2 g over L theta 1 is 0. All right, so there we go. There is actually our first equation of motion that describes the evolution of this system. All we've got to do now is consider the I equals 2 case, right? So let's do that. When I equals 2, we care about that derivative and that derivative. Remember, with the first one, we have to differentiate it with respect to time again. So we get a second dot on each of the theta dots. And we get ml squared times theta 1 double dot plus theta 2 double dot. Then we're going to get plus or minus that thing, but it's minus minus, so it's plus. So it's plus mgl theta 2 is 0. Again, if we divide by ml squared, then we're going to get theta 1 double dot plus theta 2 double dot. This time it's just plus g over L. Theta 2 is equal to 0. So we've got two equations of motion, equation 1 and equation 2. So the very last point I'd like to make in this video is that both of our equations of motion are linear, right? As we expected, because we did the Lagrangian to second order. So they're both linear in the angles and their time derivatives, which means we can write this as a single matrix equation, right? So if you think about it, the first part of each of these equations involves the second time derivatives. So if I put them into a vector like this, theta 1 double dot and theta 2 double dot, I could just pre-multiply that vector by a certain matrix whose entries would just be the coefficients of those terms in the two equations, right? So I get a 2 as my first entry, I get a 1 as the second entry, and then I get 1s from the second equation as well, like that. So I get 2, 1, 1, 1 times that vector of second derivatives, which takes care of that first part of these two equations of motion. For the second part, I can take out a g over L, right? Then I'm going to write this as a matrix times a vector of angles themselves, theta 1 and theta 2. Oops, theta 1, theta 2. Again, we can read off the entries of this matrix based on the coefficients of theta 1 and theta 2 on the equations. So the first one, well, we've got two lots of theta 1. So I put a 2 there, but we don't have any theta 2s in the first equation, so I'm going to write that as a 0. In the second equation, there are no theta 1s, so I get a 0 there. But there is one lot of theta 2, so I put a 1 there, and all of that is now equal to the 0 vector. And so there we go. We've now expressed our equations of motion as a single vector equation involving the vector of thetas and the vector of their time derivatives. Now, the reason for doing this is going to become clearer in my next video, in which I'm actually going to solve these equations of motions to see how the double pendulum evolves with time. I'm going to find certain types of motion called the normal modes. So hope you will enjoy that one as well.